How many different ways can you rearrange these letters? There's 5 A's and 3 B's. I'll leave it up for a second. But basically, if you think about it, you can, I mean, the way to think of this is, well, there's lots of different ways to think of this, but imagine you take your positions, which are 5, somehow 8 comes after 5. You've got your 8 different positions that you want letters to go into, and the number of ways to rearrange these symbols is the number of ways to pick 3 which are B's, or alternatively pick 5 that are A's, right? So if I pick 2, 6, and 8 to be B's, for example, then I get the word that goes A, B, A, B, A, B. Oop. So if you think about it, the answer is 8 choose 3, but also, so this was a slight trick question because I gave you 2 answers that are both correct. So also 8 choose 5 is also correct because, as we know, 8 choose 5 is 8 choose 3 because n choose k is equal to n choose n minus k for any n and k between 0 and n. Okay, so this is just it's a little bit of practice from stuff that we should be now getting pretty familiar with. Are there any questions about that? Good. So you might remember last time we did the binomial theorem. So today we're going to talk about something. And remember these n choose k things. We call those binomials, binomial coefficients, because they show up as the coefficient when you take a binomial like x plus y to a power. Today what we're going to look at is something called multinomial coefficients, which is kind of similar, although a little bit different. So here's a kind of motivating question, I guess, kind of related to what we just did in the poll. So suppose I've got, instead of just having A's and B's, I've got A's, B's, and C's. How many ways, or how many different words can I get from rearranging 4 A's, 3 B's, and 5 C's? And this is the type of thing we're going to focus on today. So here's one way to think about this. You can kind of think of doing it kind of sequentially, right? Imagine so this time we've got how many letters? 4 plus 3 plus 5, 12 letters. So there's 12 positions, like 12, the string is going to have length 12. How many ways, if we just ignore the B's and C's, how many ways can we choose where the A's go? So I'll ask, so does anyone maybe in the chat have an idea about that? How many ways can we choose where the A's go? I've got 12. Yep, that's right. So 12 choose 4 because 12 positions, we're picking 4 of them to be A's. Now here's the key thing is, once I've chosen where the A's go, how many ways can I choose where the B's go? Like, suppose I already know where the A's are going to be. Yeah, so we've got 8 choose 3. That's right. So so 8 choose 3. And now once I've chosen the A's and the B's, we know exactly where the C's are going to go because they just go on whatever's left. So for this one, the answer is, and this doesn't really seem to be anything different than what we've done. This is just a kind of product rule, or rule of product, right? It's just 12 choose 4 times 8 choose 3. But if we think about this, let's write out the formula for this, right? So if I've got 12 factorial over 4 factorial times 8 factorial, and that's all multiplied by 8 factorial over 3 factorial, 5 factorial. And as you can see, there's some cancellation. So the 8 cancels with the 8. So what we end up with is this nice kind of formula where we get, basically 12 factorial on the top, which 12 is the total number of things we're arranging. And then we have like the number of things of the first type, second type, and third type below. So we have 4 factorial, 3 factorial, and logos in the way, but 5 factorial on the bottom. Anyway, so this is just, if you're ever kind of dealing with these problems, that's always going to be the answer. Take the total number of things factorial on the top, and then look at how many of each type you have and divide by all of those factorials. So all the numbers down here should add up to the same thing as the top, like 4 plus 3, 4 plus 3 plus 5 is 12, and that adds up to what's on. So that's if you just want to remember the kind of trick, then this is how it works. But let's talk about a little bit more. So this is basically what I just said. So suppose that you've got A the number of A's is little a, the number of capital B's is little b, the number of C's is little c, then how many you have is, and let's say that n is equal to a plus b plus c, then the number of ways to arrange it is n factorial over a factorial, b factorial, c factorial. And you get this by saying, like, this doesn't come out of nowhere, because it is n choose a, which is how many ways to choose the position of the a's, and then n minus a choose b. That's how many ways to choose the position of the b's, and then once you've chosen those things, the c's fill up all the remaining position. So a bit of terminology. So we call these things multinomial coefficients for reasons that I haven't explained yet, but it's going to become clear in a little bit. But so remember, like, oh yeah, and the notation is, so when I write n, like I write this kind of choose notation. So it's like an n on the top, and I write a, b, c. What that means is n factorial over a factorial, b factorial, c factorial. And this is only defined when a plus b plus c is n. Okay, and also I guess I can specify that, it's only defined when a, b, and c are non-negative integers. So are these definitions clear? So here I'm just kind of telling you, so this is just notation, this is what this means. So in particular, there's a little bit of, well, anyway, I'll get to this later, but okay, so yeah, so we call these things multinomial coefficient. And yeah, this so sort of I've been alluding to that, this has nothing to do, there's nothing special about three different letters here. This generalizes to when you have any alphabet. So suppose that I've got m letters. The letters are called x1 up to xm. And suppose that I've got a bunch of numbers, k1 up to km, all of which are non-negative. And suppose that n is equal to the sum of the ki. So this is just kind of, here I'm just kind of explaining the general the general phenomena when you have more than three letters, right? So here we have m different letters, and the number of strings of length n, where the alphabet is x, and the letter, so remember xi is a letter, xi appears exactly ki times, is equal to, well, I mean, you can derive this pretty easily by the kind of, the same idea as we did with the a, b's, and c's, right? You can take n choose k1, that's the number of ways to choose where the first letter goes, like the first type of letter goes, n minus k1 choose k2, and dot dot dot, like multiply these all up, n minus k1 minus k2 all the way down to km minus 1 choose km. Okay. If you think through this in some examples, like if this looks too abstract and weird to you, it just takes a little bit of thinking. So for example, if you think about it for 4 letters or 5 types of letters or whatever, what I mean is an alphabet of size 4 or 5, then it becomes kind of clear. And then if you do the algebra, like you write out the formulas, you get a lot of cancellation. And what you end up with is n factorial over k1 factorial, k2 factorial, all the way up to km factorial. So is it clear? First of all, is it clear what I'm trying to count? And is it clear why this is the answer? Buddy. Sounds good. So if you, like this goes for everything that we do in this course. Like everything we've seen so far, there's kind of 2 approaches, right? In terms of learning it. On one hand, you can always just learn the formulas, and that'll get you a lot of marks. It might not get you all the marks though, right? So really understanding how I came up with this formula is quite valuable. But at the same time, if you'd rather, if you kind of have a difficult time understanding the derivation and you want to understand the formula, then this is it. So it's, yeah. So if you have, okay. So, and the notation we have here is that we write this, so this n factorial over k1 factorial, k2 factorial, all the way down to km factorial. The notation is like this. We use this choose notation. So it's kind of like, it's kind of like an n choose k1, comma, k2 up to km. And again, this is called a multinomial coefficient. And you can see there's actually a little bit of redundancy here, right? Because in the case m equals 2, the multinomial coefficient is just like the usual thing that we have, right? So so n choose like k1 comma k2, where So by the way, this thing is only defined when like the sum of the ki's is equal to n, right? This is just the same thing as n choose k1, right? So in the case m equals 2, there's a little bit of redundancy in the notation, like these two things mean the same thing. But when you have 3 or more different types of letter, then you kind of need a way of kind of saying how many times each one appears. So I don't know. So this is the kind of standard notation. Is that clear? Okay, so this is just mainly understanding the notation. Okay. Actually, I've kind of already done this in some sense. The algebraic proof for why this is equal to what I said it is. But anyway, let's think about it again. So yeah, so if I've got, so I'm going to have, so the letters are called x1 up to xm, right? So I've got the first letter is called x1, right? And I've got n, you know, my word is going to have length n. So the number of ways to choose the positions of the letter x1 is going to be n choose k1, right? Because I'm specifying that I need to have k1 x1s, so that letter has to show up k1 times. So I have that many ways to choose it. And once I've already chosen the positions of x1, x2 up to xi minus 1 for some I, I've already kind of taken, like, you know, for example, if the first letter is A, you know, I choose the things that are going to be A's, and now those are like off the table, right? I can't choose them again to be another letter. So the number of ways to choose where the ith letter goes, well, you've got all the positions that are remaining, of which there are n minus k1 minus k2 minus ... up to ki minus 1, because, yeah, we've already chosen or selected the character for this many positions. So I've got n minus that many left, and we're going to choose ki of them to be x, right? So the number of choices becomes, you know, it's n choose k1 times, yeah, n minus k1 choose k2, and so on and so forth. So just using the formula for binomial coefficients, you know, ... and I've got n minus all of the, well, right. The thing is, the last letter, you're not really going to have any choices, right? Because once I've chosen the positions for every letter except for the last one, you're kind of done. So I'm going to write it like this. So the last thing I'm choosing is the second last letter, and the number of choices I've got is like this. Oops. Anyway, this is really just algebra, and you get a bunch of cancellation, just like we saw in the case of 3 letters, right? Except now you have more cancellation, so it goes all the way down, and you are left with this thing. So if you want to know how many words you can make by rearranging some letters, where some letters appear more than once, this is the answer. Okay, so how many ways can I rearrange the letters? So an example of, okay, I feel a little bit self-centered or something, right? Making my own name as an example. But anyway, so how many ways can I rearrange these letters? So we have to see how many times each one appears. So I've got 1J. So if I kind of keep a tally over here, the number of O's is 2, the number of N's is 3, A's is 2, T, I've got 1, H, I've got 1. Is that everything? Nope. E, I've got 1, and L, I've got 1. Hopefully that adds up. And so the answer is 9, 10, 11, 12. 12 factorial over, and then you just write all of these factorials. So 1 factorial, 2 factorial, 3 factorial, 2 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial. Is that clear? 12. Okay, that adds up. Okay, cool. So now I want to tell you about something called the multinomial theorem, okay, which is quite similar to the binomial theorem we saw last time, but a little bit different. So I'm going to do something a bit strange now and just kind of ask you, can you guess, before seeing the theorem, what would be the coefficient of x to the 3, y to the 4, z squared in the expansion of x plus y plus z cubed? Or sorry, to the 9. What am I saying? So what's the coefficient of this thing in the expansion of this thing? Okay, we've got good guessers. Okay, I'll end the poll. So everyone who did make a guess made the right guess. Indeed, it is a multinomial coefficient. So I wrote it in the poll as like 9 factorial over whatever, but yeah, 4, 3, 4, 2. So it is this multinomial coefficient, 9 choose 3, 4, 2. And yeah, that's exactly what the multinomial theorem says. So more formally and more generally, suppose that I take a bunch of non-zero real numbers, x1, x2 up to xm, such that if I add them up, so remember we have these hypotheses in the binomial theorem, so we've got similar hypotheses here that if I add up the coefficients, or sorry, not the coefficients, but the variables, they're non-zero, then for any integers k1, k2 up to km, where they add up to n, so the coefficient of x1 to the power k1 times x2 to the power k2 all the way up to xm to the power km in the expansion of x1 plus x2 blah 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 up to xm to the n is the multinomial coefficient n choose k1, k2 up to km, which is the same as n factorial over k1 factorial, k2 dot 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 up to km. Okay, so that was a good guess. Right. And yeah, so let's kind of think of a combinatorial proof. And this is basically exactly the same thing as the combinatorial proof of the binomial theorem, but now it's just that we have more variables, which is kind of the same thing as in a word having more letters, right? So think of these variables x1 up to xm as being letters, right? And the number of ways to choose a term of the expansion. So if you do this kind of, if you think of like the distributive law for like, you know, how you do the first outside inside last FOIL or whatever, when you multiply out products of, you know, sums. If you think about it, every term in the expansion will come from picking something in the first factor, the first sum, like picking one of these variables, and then picking one of these variables, and then going all the way, so picking, yeah, so this is like in the first one, the second one, all the way up to the nth sum, and in each of them we pick a variable. And that's basically how you get a term of the expansion. That's if we don't collect like term, okay? So if we just kind of, yeah, so that corresponds to words, right? If I take, it's basically the same as saying I pick a letter for the first one. Think of x1 up to xm as letters. Pick a letter for the second, all the way up to the last. And the word you get, if you kind of, now once you've written the word, you can collect up the factors which are the same, right? So if I've got 5 x1s, I can write that as x1 to the power 5, right? And so once you collect everything and you collect all the terms together, the coefficient of this thing is going to be the number of words of length n with, you know, k1 x1s, you know, k2 x2s. Yeah, the s here means plural. It's, the notation is kind of crap, but all the way up to km xm's. I don't mean k2 times x2 times s. Anyway, the or I should say where the, you know, the, in other words, the ith letter appears. What I mean is the ith letter appears ki time. That would have been a better way to write it. And we know what that is. It's just the binomial coefficient or multinomial coefficient n choose k1 and k2 up to km. So that's a proof of the multinomial theorem. And this is really basically the same thing. I guess you can probably tell that it's almost the same thing as the binomial theorem. But now we can deal with things which have more than one variable. Is this clear? Are there any questions? So if you didn't understand the proof of the binomial theorem, now you've had a second chance, kind of, because this is basically the same as the combinatorial proof. I also gave an algebraic proof using Pascal's identity, but yeah, this is the same as the combinatorial proof. Okay, was there a question? Do we remember Pascal's identity? I now keep reminding you of this over and over and over, but it's very important, so you should remember it. So Pascal, remember it says n choose k is n minus 1 choose k minus 1 times n minus, or sorry, plus n minus 1 choose k. How does that work for multinomial coefficients? Like, is there a kind of Pascal for multinomials? And the answer is yes. So it turns out if I take, so here's the kind of version of Pascal's identity for multinomial. What you do is you take n choose a, b, c, that's equal to n minus 1 choose a minus 1, b, c, plus n minus 1 choose a, b minus 1, c, plus n minus 1 choose a, b, c minus. Can anyone, so this is asking for a bit of audience participation, but can anyone give me a reason why this is true, either in the chat or by unmuting? This sound effect is relevant again. Yeah, that's fine. Yeah. That's a good question. there's something, this is a bit of like kind of confusion that comes from the notation. Like unfortunate, like the notation kind of, it causes some problems because remember, so n choose k, if you write it in the usual way that we've always been writing it, and that the way that everybody writes it is just n choose k. But if you write it in this multinomial way, it's also like n choose k comma n minus k. So what this multinomial kind of Pascal thing would be saying is that this is n minus 1 choose k minus n minus k plus, so like where I reduce the first one first, right? That goes to a k minus 1. And then I reduce the second one. But yeah, this is a very good question. Worthwhile to think about. It's basically, the notation, it causes some confusion. It's not my fault because this is very old notation. But anyway, so so when if I kind of follow the pattern that we've got up here, but with only two things in the bottom, I would subtract from the first one and then the second one. But this actually is just equal to n minus 1 choose k minus 1, the first one, and n minus 1 choose k. So it's not a contradiction in some sense. It is the same thing. It's just kind of in disguise, which is kind of annoying, but that's a good question. Thanks for that. Okay, so maybe I'll give a reason then if nobody wants to volunteer. Basically, so imagine I'm arranging the letters A, B, and C, right? That's what this thing counts, this n choose A, B, C. Like I've got A, like little a capital A's, let's say, little b capital B's, and little c capital C's, and I'm arranging them. And basically this formula comes from looking at what is the last letter, right? So if I say how many ways can I arrange the A, B's, and C's so that the last letter is A? And I claim that it's this. This counts where the last letter is A. Why? Because if the last letter is A, I think the answer in the chat is explaining what I'm trying to say here as well. That so if the last letter is A, how many ways can I? So the number of choices is just the number of ways to fill in, the smaller word that comes before the last letter. So that's n minus 1 positions, and there's going to be a minus 1 A's in that shorter word. And this just counts the number of ways for the last letter to be B by the same argument. And this one counts where the last letter is C. And of course, in a word made up of A, B's, and C's, A's, B's, and C's, the last letter has to be one of the three options. It can't be two of those options. So by the rule of sum, this is actual equality. Anyway, so more generally, so do I put the more general version of this? Maybe not, but I think it should be clear now how this works more generally. Like if I've got a multinomial coefficient where it's like n choose k1, k2 up to k100, you reduce, you take n, that thing is equal to n minus 1 choose, k1 minus 1, then k2 up to k100, and then you just kind of sequentially reduce each of these things by 1, and you add them all up. Is that clear? Okay, so let's practice. So what is the coefficient of x cubed y to the 5 z to the 6 in this lovely expression? 2x plus y minus z, 2x plus y minus z squared, all to the power. And I understand that one issue with these poles is like simply parsing the math expressions that are in them, which is kind of annoying. So sorry about that. But basically, if you kind of work out what the answer is, then you can probably find which of these ones it corresponds to. Yeah, the parsing the math is not. Any more kind of responses? We've got a tie so far in terms of what people think. Not a tie anymore. Maybe I'll start doing it while people think. The way I would suggest doing this, like if you want a systematic way of doing it, where like as you get better, you might be able to just pick off the answer like that, just like kind of see the pattern. But when you're kind of learning this, might want a kind of systematic approach. So what I'm going to do is do a substitution. So I'm going to let A be 2x, B is y, z, or sorry, not z, I've already got a z. C is negative z squared. So basically the expression I'm looking at just becomes a plus b plus c to the 11. And basically like the thing I'm looking for is like I want x cubed y to the 5 z to the 6, which is like kind of the coefficient when a, you know, when you've got a cubed, b to the 5, and c cubed, right? So the coefficient of a cubed, b to the 5, c is, as we know, it's 11, choose 3, 5, 3. But then we can plug in our z's again, or x, y's, and z's. So when I've got, like, this thing is equal to, well, a cubed is 8 times, or 2 cubed times x, right? So, well, I'll just maybe, I won't skip steps, I'll just do this. So, and so what you get is the negative, it's cubed, so it stays negative. And you've got, so negative 2 to the 3, x to the 3, y to the 5, z cubed. So basically the coefficient I want is like the combination of these things. It's so it's this multinomial coefficient times negative 8, or negative 2 to the 3. Okay, so by a slim margin, the majority got that. Yeah, you've got to, so one important thing is like really understanding what the question is, I think, here. You have to be careful, right? If there's coefficients on the variables, like a negative and you know, 2, for example, you've got to be careful, because I'm asking for the coefficient of x cubed, y to the 5, z to the 6, not like, if I do the substitution with a, b, and c, I'm not asking for the coefficient of this thing, like a cubed, b to the 5, c to the c cubed. I'm asking for the coefficient in terms of x, y, and z. So, oh, sorry, this here, there was a little bit of mistake here. That should have been z squared, so that's z to the 6. Anyway, is that clear? So don't get fooled with these things. Do substitutions and stuff, because that's the easiest way to figure it out. Any questions at all? No? Okay, maybe this is now getting a bit redundant. So maybe I was going to ask you to answer this in the chat, but, well, you can still answer it in the chat if you want, if you're faster than I am. But how many ternary words are there with R0s, S1s, and T2s? Remember, a ternary word is a word with alphabet, so that's the alphabet, 0, 1, and 2. How many ternary words are there with that many ones, zeros, ones, and twos? Actually, maybe, yeah, if anyone can think of it and write in the chat. Or, so it's really not much different from what we've been doing, right? It's just sort of, I've been usually writing A, B's, and C's. Now we just have zeros, ones, and so, yeah. So the answer is going to be R plus S plus T, kind of choose. I don't know if people use the word choose for this or not, but anyway, the notation is like this, right? So, or if you wanted to write out what it is algebraically or whatever, it's this. Okay, so let's maybe, yeah, okay, why not this one? So, because I keep on using examples where there's only 3 different types of symbol, but now we've got 4. So what's the answer here? Actually, maybe I'll just quickly say this one. So we've got 25. So we're looking for a word of length 25. So the numerator, well, okay, the top of the multinomial coefficient is 25. We're picking 6 A's, 7 B's, 4 C's, and 8 D's. And so it's this. One thing to maybe I should make completely clear is that if you wrote something like 25 and you wrote these in a different order, 7, 6, 8, 4, that's not wrong, okay? So just so you know, like the order of the things at the bottom doesn't matter, because you get the same number anyway, because if you look at the formula, you'll see that it's the same. And this is kind of remember this like fact we keep mentioning, that n choose k is equal to n choose n minus k? That's kind of the same thing. So, right, n choose k is n choose n minus k, right? If we write this as kind of in this multinomial notation, what this would say is that n choose k n minus k equals n choose n minus k, right? So switching the things doesn't make a difference. And that's the same thing that's going on here, that if I take any, something choose k1, k2 up to km, and I switch around these ki's in some way, it doesn't change anything. Is that clear? So you'll never get marked down for having the things in the wrong order, because there isn't any wrong order. Everything is the same. Okay, so here's a question. So the UVic Enumeration Club, which is not a real club, I'm sure all of you would be a part of it if it was. I'm just kidding. So it has n members, okay? How many ways can I choose k of them to form, oh yeah, a committee on binomial coefficients. So, you know, because this club really needs such a committee, and R of them to form a committee on derangements, which is something coming later in the course, such that no member is in both. So you can ignore all this the story here really, but you've got n people. You're putting k of them into one club or one committee, r of them into another committee, and nobody can be in both committees. So how many ways can you do it? And well, and yeah, we've got this assumption. It only makes sense if r plus k is at most n. Otherwise, you know, if r plus k is bigger than n, you can't possibly make these committees because there's not enough people. Well, almost. So there's an answer of n choose like kr. Yeah, that you need. The thing is that, and that's the kind of problem with this notation. I don't know, but yeah, you need to write three different things because yeah, if I write this is not actually kind of defined in a way, because if I wrote n choose kr, that doesn't work because k plus r is not equal to n, right? And this would only be breaking. This would be like, yeah, you've got kind of two types of people, right? The ones in the first committee and the ones in the second. But actually, we've got three types of people, right? We've got the people in the first committee, we got the people in the second committee, and we've got people who are in no committee, right? So you have to think of all three kind of types of people here. So the answer then is n choose k r n minus k r, or sorry, n minus k minus r, which is the usual thing. And I mean, you could deduce this by, you know, just because we've talked about this, we, you know, by the discussion we've given, but you could have also just come up with this in a different way, right? By just saying, okay, how many ways can I choose the first committee? Okay, it's n choose k, right? How many ways can I choose the second committee? Well, k of the people are already gone, so I've got n minus r or n minus k choose r, and that would actually give you the same answer. So, you know, so in some sense, everything we're doing today is kind of follows from everything we've done before, but but it's still valuable to understand these multinomial coefficients so that you don't have to go through the steps every time of deriving them. Is this example clear? Thanks for the participation. Okay. Yeah, this is just kind of, we just keep on kind of repeating the same thing, kind of beating a dead horse here. But yeah, so I've got n different objects. So the fact that the objects are different matters. Okay, first of all, that these are distinguishable objects. How many ways can I put them into m groups where the sizes are? So, but first of all, I should point out, if I just wanted to put them into m groups and I don't care how many go into each group, what would I get? So maybe I'll ask this to you. Suppose I've got n distinct objects. Let's say first, we don't care, you know, so m groups of any size. So I don't care how big each group is. Like they can even have 0 in a group. So what would I get for that? So this is a bit of a review, but actually I should say that the groups of things are sort of labeled. So like I've got the first group, the second group, the third group, and so on. Yeah, because otherwise I don't want to make that too ambiguous. So yeah, the group, I'm going to put some of them into the first group, the second group, up to the nth group. So if the groups have any size, so this, I think this answer in the chat is coming from, so this is a good guess of n minus 1 choose m minus 1, but it's not quite right, because remember, so that remember this like cookie thing we were giving cookies to children, and we kind of had, you know, n minus 1 gaps and stuff when we were putting things in the gaps. That is good if all the objects are identical, right? Otherwise, if I've got different items, so I've got a boot. I don't know, for whatever reason, that's the first type of item that comes to my mind. A boot. What else is an item? A fork. A stick. Okay. And if I had this dividing line argument, if I put a divider here, like you're always going to get the boot coming together with the fork, but that's not quite, you don't want the boot to always be with the fork. Well, okay, it won't always be with the fork because there could be a divider here, but you see what I mean? Like I want to allow more variations. So there's another answer in the chat, which is the right one. And so this is, yeah, it is important here though that I say that these groups are like labeled groups. But anyway, that, yeah. But yeah, so the answer is m to the n, right? Because I just go through every item one by one and I say, which group are you in, right? So I say, I've got m choices, I've got m choices all the way down. Okay, but this is a nice thing to think about to understand the difference between these two different types of problems, right? So if you have distinguishable objects, it's different than having indistinguishable objects like some identical cookies or something. Okay, but now if I want the items to have specific size, or sorry, the groups to have specific sizes, k1 up to km, then the answer is n choose, or the multinomial coefficient where you have k1, k2 up to km on the bottom. But yeah, if I don't care about the size, the answer is just m to the n. So this is a kind of combinatorial argument for kind of saying why two different things are equal. So suppose I've got 8 people. I'm breaking them into groups of size 3, 3, and 2. And again, these are sort of labeled groups in the sense of like, one group is, let's say, committee 1, the other group is committee 2, and the other one is committee 3, for example. So I care what the name of the group is in some sense. And I claim that this is the same as the arrangements of these letters, right? Which is something we're kind of observing here, but just to make this clear why these are the same thing. Yeah, so imagine I take the people, I put them in a line, okay? And in order to determine who goes in which committee, I have a very kind of, a funny way of doing it where I give people a hat which has the letter of their committee. Okay, so this is my crappy drawing of a hat here with an A on it, right? And imagine I line these people up left to right, and I give 3 of them a hat that has an A, 3 of them get a hat that has a B, and 2 get a hat that has a C. And they put these hats on, right? And if you think about it, if I read this from left to right, that's going to make a word if I read the hats. And so basically breaking people into committees in this way is the same as writing a word, basically, if that makes sense. Okay. So this is just trying to connect these concepts. Like for some people, certain versions of this might be easier to understand, and for others, other kind of phrasings might be easier to understand. But this is just trying to show that all of these things are kind of the same thing. Okay. Okay. Question: how many ways can 3n people? So the number of people is 3 times n. And what they're going to do is pick a vice president, and a treasurer. And then once they do that, they're going to divide up everybody else into 3 committees of the exact same size. So all the committees, have the same size. How many ways are there to do this? Any thoughts? As most things in this course, this kind of boils down to the rule of product, right? But first of all, how many ways can I choose the president? So in these things, you should often think of doing things sequentially, right? First, I choose the president. I've got 3n choices. Then I choose the vice president, 3n minus 1 choices. Then I choose the treasurer, 3n minus 2 choices. And then I'm going to break the rest of them into groups, into 3 committees. So how many people do I have left? I've got 3n minus 3 people left because the 3 special people, the president, vice president, and treasurer, they're not in the committees, right? And then I break them into equal groups. So each group has a size n minus 1. And so that's going to be the answer. Any questions about anything? Let me then do a poll. So this is a kind of reverse question where I want to say, I'm going to say, so I say, I've got this number, 9 choose 2, 4, 3, or the multinomial coefficient, 9, 2, 4, 3. Which of the, so I haven't written these on the slide, I've just got them written in the poll. But so here you can now choose multiple answers. Which of the numbers are equal to 9 factorial over 2 factorial, 4 factorial, 3 factorial? The number of strings of length 9 with alphabet 2, 4, 3. The number of ways to arrange A, B, B, A, C, C, B, C, B. Number of ways to take 9 identical donuts, put them into 3 different boxes of sizes 2, 4, and 3. Number of ways to break 9 people into 3 groups of sizes 2, 4, and 3. None of the above, or as usual, there's always the option to say that you don't know. Yeah, so what are the answers here? So remember, you can choose more than one. So first of all, maybe we can just kind of answer some of these things rather than, just telling you which ones are and which ones aren't. So what is the number of strings of length 9 from the alphabet 243? Any answers? Anyone know? What I need is like the Jeopardy soundtrack or the Jeopardy song. Do people know Jeopardy? Like, anyway. We got an answer in the chat. It's kind of the reverse of what that answer was. So again, the length is 9. You've got 3 choices for each. So 3 times 3 times 3, blah, 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 up to 9. So it's 3 to the 9. Okay, so that's actually, so then we know that one's not the answer, or that's not a right answer. Because you can check these things are not equal. The number of ways to arrange ABB, so arrange ABB, ACCB, CB, which is quite an annoying thing because I've put them all in the weird order. So how many B's we've got? Do we have, we've got 4 of them. We've got how many A's? We've got 2, and we've got 3 C's. So this one's going to be a correct one, right? Because this is what we've been kind of talking about quite a lot. It's the number of ways to rearrange these things: 9 factorial, 2 factorial, 4 factorial, 3 factorial. So that one is correct. Putting 9 identical donuts into 3 different boxes where the boxes have size 2, 4, and 3. Like the first box can hold 2, the second can hold 4, the third can hold 3. The thing about this one is that the thing to notice is that the donuts are identical. I think there's always a bit of ambiguity in these things, right? That, what do I mean by the donuts are identical? I mean that you can't tell the difference if say I take a donut out of the first box and donut out of the second box and I switch them, you can't tell the difference. So actually for that one, there's actually only one way to do it in some sense, like, because you can't tell the difference between anything you do. So that was, maybe it might feel like not almost unfair, but this word identical is important. So when you see questions that use the word identical, that means that, if you change them, you can't tell the difference. So those are considered the same solution. So actually, with the donuts, there's only one way to do it. I put 2 in the first, 3 in the second. Like, I can't, if I change which donuts go where, I can't tell the difference because they're identical. So it's important in these questions when they use the word like distinguishable or identical to know what they mean by that. So actually the third one, the answer is 1. There's only one way to do it, weirdly enough. So that one's not a correct answer. Third one, number of ways to break 9 people into groups of size 2, 4, and 3. That one is a correct answer. So that's 9 factorial, 2 factorial, 4 factorial, 3 factorial. And you can see this in many ways. For example, thinking of them as words, like I said, you can think of giving them hats that spell out a word. Any questions about that? So maybe people didn't like the donut one, but it's important to understand this distinction. Just one way, and that's kind of like the cookies. Remember these cookie things? I said you have identical cookies and we're distributing them. And so basically all that mattered, like all you had to do is put divider lines, because if I divide the cookies into like a set of size 2, 4, and 5, right? And if I switch the cookies between those groups, it made no difference because they're the same. So it doesn't matter which cookies go where, it just matters how many. So that's why these divider lines worked. Whereas, once I've already told you how many go to each child or whatever, like if I switch them, it doesn't matter. They're all Oreos, right? Oreos are just made in a factory. They all look the same. So, okay. Let me, because we've got a few minutes left, just kind of formalize something which I didn't actually say before. But we've kind of talked about this idea a little bit, but kind of in disguise. First of all, remember this identity, 2 to the n equals the sum k equals 0 up to n choose k. There's a similar thing for multinomial coefficients. So suppose I take the sum over all, let's say a and b, where a plus b is n. Or, okay, maybe to make it clearer, although it's hard to make this incredibly clear, but let's say I'm summing over all a, b, and c, where a plus b plus c equals n. So this is just saying, what if I sum up all of the multinomial coefficients for n that exist, right? Because remember, whenever we have n choose a, b, c, they have to add up to n, right? So what should this equal? Any thoughts? So there is a natural guess, I think, but not just guessing, but understanding why is also kind of important. But yeah, the answer is 3 to the n. Why? Well, this counts all the ways of breaking up. So it counts ways to divide n people into 3 groups where where these groups add up to the size of the groups adds up to n. And this just this counts the same thing, except where so this is 3 groups, again, n people into 3 groups of sizes A, B, and C. Okay, and again, the groups are always like labeled, like it's group 1, group 2, group 3. Yeah, so and then if you sum over all different A's, A, B's, and C's, then that'll count all the ways of doing it into 3 groups. There's another way of seeing this, which is algebraic, right? Because the multinomial theorem, right? So if I have x plus y plus z to the n, by the multinomial theorem, this is the same as summing up over all a, b, c, where a plus b plus c is n. N choose a, b, c, x to the a, y to the b, z to the c. And so a second proof of this is that if I just let all of the x, y, and z be 1, and the left-hand side becomes 3 to the n, the right-hand side becomes the sum of these coefficients. Okay, so these become the same. Do that. And similarly, if I take the sum over all the multinomial coefficients, let's say a1 am equals n, n choose a1. So I should in these things maybe be saying that these are non-negative. So this is always going to equal m to the n. So there is a connection between this problem of breaking into groups where you don't know how big they are and breaking into groups where you've specified the sizes. Okay, so are there any questions about this? And actually similarly, remember when we were dealing with the binomial theorem, we did all these tricks, right? By plugging in different values of x and y and z. Well, and now we have more variables. You can do some similar tricks using the multinomial theorem, right? You can plug in different values of x, y, and z, or different values of, you can have if you have m variables, you can plug in different values. You can take derivatives, you can take integrals, and you get all these different identities algebraically. Okay, so I think that's all I wanted to say. Are there any questions? Yeah, sure. Yeah.